reached critical mass, and so I think we should perhaps get started. Good afternoon. My name is Gary Baldwin, and I'm the Managing Director for I4Energy, and also am involved with CITRIS. Welcome on behalf of all of those organizations, and welcome to those of you who are viewing this presentation on the web, especially our sister campuses of CITRIS at Merced, Davis, and Santa Cruz. Let me thank the sponsors of the lunch, the California Institute for Energy and Environment. We're always very, very grateful for their support. And remind you that we have not one more, as announced in the program, but two more seminars this spring. There's an extra one that we're adding at the end by Christine Ho on April 30th. It will be in room 250 downstairs, and the topic will be flexible storage systems, that is, flexible batteries and storage systems that are appropriate for solar energy. So we'll get out an announcement on that pretty soon. Today it is our great pleasure to have Professor Carlos Coimbra from UC Merced here talking on a topic shown on the screen, solar forecasting. Carlos has his bachelor's degrees from Brazil. He is from Brazil, did his master's work in Portugal, and received his PhD from the University of California in Irvine. His specialties include heat transfer, small particles, and he's now extended that and extrapolated it, as you see, to solar irradiance measurements. I might just point out, for the benefit of those here in physical presence, that Carlos is also a master in martial arts. So you might want to take that into consideration during the question and answer period at the end. So,
how do you know that?
How do I know that?
Who told you?
I can just tell from the way you move. So let's give our usual warm welcome to Professor Coimbra.
Thank you. Thanks, Gary. Is this working? Can you hear that? Okay, good. I'm going to start by, I brought this. Gary and Jeff have seen this a million times, but this is an interesting picture. I went to a conference about 2 years ago, Solar Power International, and somebody put this up and gave an interesting talk about this. And I find this fascinating. I'm always fascinated by the response that the students give when I show this picture and I ask them to comment what is unexpected in the picture. I had people comment on the fashion of saying that these people here in black don't like the people there in white, this kind of answers. But the fascinating thing here, can anybody guess what it is? Yeah. So this is a 1905. This is a California bungalow in a neighborhood of LA, and at that point, the interesting fact is that many houses, more than half of the houses in many of the neighborhoods in LA had solar heaters. Sorry?
You know the name of that system?
No, I don't.
It's the Climax.
Climax. Great. I have something else to talk about. So this is going to continue to be my picture for the next 10 years. I would guess that this is a fin and tube a system, just like the one that you could buy, you can buy still today, even though technology has changed a little bit. So I'm not here to talk about solar thermal heaters, but the bottom line is that if you think about it, why you came from a situation where you had 50 or 70% of your water heating being done by solar collectors, and you went down to a number that's very close to zero. If you drive around today, if you drive to the Central Valley, which is a fantastic place for solar resources, you'll be hard pressed to find one single solar collector in thousands of houses. U.S. today has less than 0.5% of the installed area of solar thermal heaters in the world. If you compare this with China, China has 80%, almost 80% of the area installed. It looks like we came a long way from 1905, but in the wrong direction. So why this happen? Of course, there are several reasons, but the main reason is because how many of you have solar collectors in your house? One? One. That's very typical. Two? That's actually very typical. This is a great response. Normally when I talk, there's only one person in the audience. And most people are very satisfied with their systems. But there is a pervasive impression that solar energy is not reliable. And it's not reliable because the solar resource is intermittent. And there is a particular problem with the solar water heaters, and I'm going to be talking about power today, but the particular problem with solar water heaters is that if you live in a place where the winter is cloudy and cold, you would be thinking that, like, well, this is the time that I want to have my hot water, and the hot water will not be available, right? This is not, like, always the case, but, like, this, I think, is responsible for most of the decline in use of solar heaters. Financially speaking, solar heaters pay off, like, very fast. Like, the financial payback time of solar heaters is, in most places, like, within a year. So there is no rational reason not to have it. But here I'm showing, like, this is a very busy graph. Like, and if you're in the back, you may not be able to see everything. But, like, these gray areas here are just the amount of irradiance, the direct normal irradiance arriving in Merced, in our sensors, during the month of March, which is actually not a pretty bad month, but is the end of a very bad season for Merced. So if you look at how much this oscillates, like, these are the integrated amounts per day in kilowatt hour meter square per day. So each one of these points is 1 day. So you can have 1 day with, like, pretty high, 10, close to 10 kilowatt hours per meter square. And then this can drop, like, to virtually zero in days that you have, a lot of clouds. Particularly sensitive to this is what we call DNI, the direct normal irradiance. We're going to be talking a lot about this. So I better explain a little bit of what it is. There are two types of energy coming from the sun that are very relevant to my talk today. One of them is it's called DNIs, direct normal irradiance. This will be the solar energy that you would receive if you take a paper towel tube and you look at the sun directly. So you would have to track the sun, and that would be like the direct radiance that's coming from the sun. Very sensitive to cloud cover. Like, if a cloud comes in front of it, like, DNI goes virtually to zero. The other type of energy would be, which, like, includes the DNI component, is the global horizontal irradiance, which is like the amount of irradiance that arrives on a flat plate that is left horizontally, right? So if I go to Merced, for example, and I make some measurements of 2 consecutive good days, like, I would get something like this, which is like the red line would be the direct normal irradiance. It's tracking the sun, so it's getting, like, the best out of the energy, and then this is the night, and then this is the next day. So this is for some time in August of 2008. Very predictable. You could use this energy, like, there's a lot of quality in this energy. But then when you get into September, like the end of September, like, you have a very good day. The next day, like, you start having clouds, like, you drop, you lose, like, about 30% of the energy that's available from the sun because of the cloud cover. This graph here just shows, like, the average March day. So we took all 31 days and we added them up and divided by 31. So this is the average day of a March, like a pretty reasonable maximum direct normal irradiance, DNI. And these two other lines are like the 75% confidence level, meaning 3 out of 4 days are between this very large range of irradiance. So if you think about, like, solar technologies today, like, you can think about, like, what are each one of these different competing technologies are trying to achieve, and you can simplify, like, an analysis if you think about, like, 4 different quantities. Like, the real cost of solar, of course, like, one of the major impediments to have, like, a solar used, like, broadly is, like, the price. Like, so what's the cost of your kilowatt hour? Like, what's the capital investment? What's the energy payback time? How long does it take for the solar power technology to pay back to the grid the amount of energy that was spent to create the technology? And the financial payback how long does it take for you to recover your investment. Another very important point is the storage. Like, and the storage is like, really strongly connected to the predictability. Like, if you can have like quite a lot of storage, efficient storage, you would be able to, attenuate the fact that solar energy is not considered to be, is an intermittent source. And then, of course, like, you want to have like a high efficiency, because efficiency can generate the opening to better technologies that are more expensive if you can actually reach higher efficiencies. So today, like, if you forget about cost, which obviously nobody wants to forget, but like, I can have a lot of storage if it costs a lot of money. So if you forget about cost and you try to understand this in a little bit more easy way to see it, I can pretty much like, put like different technologies, solar technologies, into three axes, like where this going vertical here is the quality of energy intensity times efficiency, storage capacity, and forecastability. Right? I'm not sure that this is like a real word, but like, I think you understand what this means. So most of the technologies that are in red here, these technologies in red, like, they depend on DNI. They are concentrated technologies. They depend on the highest quality of solar irradiance. Typically very difficult to predict because it's so sensitive to cloud cover. But like, it's where you get like the highest temperatures, like in the highest concentrations, like, they are all here. So this will be solar thermal power, solar Stirling engine, and concentrated PV. So all of these technologies, like, they are actually pressed against like the axis of forecastability. So they are living in this plane of storage and quality of energy. They have very high quality of energy. Solar thermal power has like a very good capacity for storage. But like, for them to become marketable, they would have to advance and get out of the origin of these three axes. So we would have to have more forecastability, so like we can actually connect these technologies to the grid in a large-scale fashion. I separated here in orange tracking PV, because tracking PV use both global, horizontal, and like a DNI. Like, it's technology that tries to take the best out of both worlds, right? And then the lower quality energy, like the fixed PV and the solar water heaters. Here you see like solar water heaters, like pretty reasonable storage capacity. This is not to generate power, but like is to generate like a hot water. And like relatively easy to forecast, because they depend more on latitude inclined irradiance. A major shift here, and that's one of the reasons why China has so much of the installed area, is the shift between like the regular fin and tube solar collector to the vacuum tubes. And what this did essentially was like to increase the quality of the energy, because you are actually heating up, like you can get more of your energy. You have much less like thermal losses, and you can store at higher temperatures. So basically what we are trying to do is like looking at these technologies here that like seem to be in the forefront of what is large-scale production of a solar, and then increase their capacity to become marketable by better forecasting. So when we started this, and I want to have a little plug for CITRIS here. Like CITRIS had a major role in this research. We got, I think, about 2 years and a half ago or 3 years ago, we got a seed grant from CITRIS, regular size, $75,000, but like it looked like a small amount, but this allowed us to buy some, the first instruments that we had. We installed these on campus. We have 2 stations, one at UC Merced, one at Davis. And this was like originally funded by CITRIS. Since then, like we got like a couple of $1 million from several different sources, but was really like the vision of Gary, Paul, and Jeff that helped us move this research from just talk into something, right? So we had some major high-level research questions. It's like how can we model and forecast the solar resource? Like obviously this is one thing that you want if you want to say that an intermittent source is reliable. And how can we use this detailed knowledge to better manage solar power utilization? So load shifting, like a deferred non-essential loads, like avoid demand use charges. I'm going to talk about this because we are actually installing and this forecasting process into our management system at the UC Merced. Can I use thermal storage for cooling and heating? Like how can we handle this advanced knowledge better? And how much can we reduce the cost of intermittent resources? Spinning reserves, install capacity, this is basically for the utility companies, right? So if you have like a large power plant that like, you don't know what's going to happen over time, you have to keep like, a spinning reserve going all the time. This adds to the cost of solar energy, right? So like how can we decrease that uncertainty so that we can actually decrease both install capacity and the spinning reserves for utility companies, right? So there are several different strategies, like, and I talk about like 3 here, like, we actually do all 3 of them at UC Merced. I'm going to be concentrating most on the hybrid. The satellite-based, of course, this is look at the images, like, satellite images like I used for a long time for weather forecasting. You process the images, like and typically you use like transmittance models, like these are typically deterministic models. It's very good, like, offers like a fantastic area coverage, but has the major problem of having a poor temporal resolution. So like you don't get like images like every second, and if you would get, like, they would be like extremely expensive. You have to deal with a very large amount of data and data processing. Also, like there is like the issue that like the models are mostly deterministic at this point. Like they are simple transmittance models. But we do use this, and we use like what I think like a smart ways. Like we use like quite a lot of satellite information in our forecasting. Then the opposite of that, like the most like the other side of the spectrum would be ground-based technologies, like these forecasting strategies. This would be just having your instruments where you want to forecast, and you take very good data, like at very high temporal resolution, and you are free to use like all kinds of different methods to try to do that. The problem with this is that like it's difficult to forecast for a point if you don't have information from the surroundings. For example, if there is like a weather system coming from some different region, like if you're only collecting data in a particular point, like you may not be able to catch that. So typically you want to have like some kind of a triangulation and a combination of these 2 forecasting strategies. And that's what like we call like a hybrid forecasting strategy. So this attempts to combine the best from both satellite and ground-based, and allows you to use different strategies, like it's a suite of strategies of forecasting that go for forecasting for 5 seconds all the way to forecasting for 5-6 days. Just to give an idea of what like a satellite-based forecasting model would be, like you would have like your raw satellite picture, and like you would have different transmittance models for each one of the components that would take out like the beam, and then you treat these in like in a geographical information system, like your regular GIS tool, and you create a solar model. And this solar model, again, like typically is deterministic. Like we are trying to implement a stochastic model into our satellite-based forecasting. And then you typically want to benchmark these with the ground experiments so that you can actually refine your model for whatever region you have. Most satellite models are very poorly validated. And then you end up like with a solar irradiance model that like can actually cover the whole state or like the whole country or potentially the whole planet, right? So then you can make this available through like a map server, and then available to the utility companies, to the California ISO, energy traders, power producers. This is more or less like the general idea about like a satellite-based forecasting models. This kind of a result that you get, you get these typically every 30 minutes, and they are typically if you use GOES West, which is like a popular satellite for this kind of prediction, they would be at the 15 and 45, but you can interpolate these and have your solar maps going on. This is not a particularly good day for solar. I think the highest DNI is in the 600s, so that's much less than what we get, for example, in the Central Valley during the summer. So I'm going to try to go through like the few requirements that we need to develop like a forecasting strategy, and then I'm going to show the results that we have and how we changed, like we upgraded our forecasting methodology. One thing that you really need like is high quality ground data. This is the garbage in, garbage out principle. Like, if you are validating everything with bad data, like, like your models are going to be bad. The caveat to that is that if you are using artificial neural networks, which is like, what normally is done with stochastic models, you can get away with precise but non-accurate measurements, because like the neural networks will pick this up. But if you just have bad data, like, like your results are going to be bad anyway. And this is going to be reflected in the root mean square error between the forecasted and the measured when you get there. You need a good method to develop efficient and versatile like artificial neural networks. This is the standard methodology that is used when you have a lot of data, like in this case. We have to overcome the typical neural network issues, like avoid overtraining, develop like neural networks for prediction, not for data fitting, season specific inputs, like that's very important. And the window of time that you're trying to forecast also requires like a selection of inputs and treatment of inputs differently. So if I'm forecasting for 1 minute ahead, I would need like a different type of neural network and a different type of input. If I am forecasting for 6 days ahead, like, the inputs are completely different. I need an overall stochastic method that's adaptable to cloud cover dynamics. Like, that's another major issue, particularly with direct normal irradiance. And I need a standalone stochastic algorithm that can monitor and continuously upgrade. Like, as you know, solar measurements are expensive. And like, there are very few good solar measurements available. If you take a series of 2-3 years, like that's very precious, like of high quality solar data. But like there are cycles, like this is climate, like it's weather, and there are solar cycles. So all of these things, like would come up, like and you have to have your method continuously being updated. I want to talk a little bit about the difference between modeling and forecasting. Like, if the first question that comes to mind is, if you want to understand the solar irradiance, like, you first want to understand what are the variables that affect solar irradiance. So then you may want to start by modeling. So modeling, you say, okay, this is what I have of solar irradiance now, and these are all my meteorological inputs, all my different like sensors that I have, and I'm going to try to correlate like that current input with the current values of my variables. And typically, you can do a fantastic job in terms of modeling. We routinely get, with the more advanced models, we get R-squares of 99.9%. So like we can actually capture really complex behavior from one day to another if I have the right inputs here. Most of the inputs for these modeling graphs, I don't know if you can see in the back there, probably not, but there are two lines here, one dashed and one continuous, like, and the dashed line is measured, like the continuous is modeled. So they follow pretty close. Occasionally, they diverge a little bit. Forecasting is substantially more difficult, but there's one advantage in forecasting is that like you can use the current value of the variable that you are trying to forecast, in the case here, a direct normal irradiance, as a predictor for the future value. So this typically is a very strong predictor, like the current value of your variable. You also need to treat the data very carefully. Like this is like an interesting graph. Like I don't think you guys can see in the back, like the details of what's written here. So I'm going to read. This is a DNI. These are 2 days. 1 day in May and 1 day in October. So like this, the red line is May 23rd, and blue is October 22nd. So basically, what you're seeing there is like is the effect of the season. Like as you're getting like, you are close to the summer solstice, like, you have, like, this, like, a larger amount of energy, like, the bulker amount of DNI available. And then as you progress, like, you're getting way into the fall here, this is reducing. So if I just, like, a brute force, like, go and try to model all of this, I'm going to spend quite a lot of my neurons trying to capture, like, the seasonality. But I can treat this, like, I can make this, like, this is equivalent to a scaling treatment of all my input data. And I can reduce the changes of DNI to only, like, the real stochastic changes. And I can do this, for example, in this case here, we do with the solar hour. So we have to do this for all the particular variables that we want to include in our simulations. Here, for example, input variables are normalized hour angle, temperature, global horizontal irradiance, which is relatively cheap to measure, the diffuse horizontal irradiance, not that cheap to measure, ultraviolet irradiance, infrared. This is long wave infrared. And the cosine of the zenith angle, like, that would give you, like, basically the altitude of the sun at that particular time. Then you're going to treat all of these entries, and you're going to try to select, like, what entries give you, like, the best neural networks for modeling. And you can get, like, really nice R squares, really effective models before you're forecasting, right? This is a graph, like, it just shows, like, like a complicated day. So these are all clouds. Like, we log data every 30 seconds. We take data every half a second, and we average the data over half a minute. And you can see, like, the tremendous variation in global horizontal here. This red line there is the infrared. Infrared is a very good indicator of cloud cover. Like, when you have clouds, like, the long infrared, like, would show you, like, a higher temperature. The clouds are much higher temperature than the deep sky. So here the same, like, you can see this clearly here, like, the infrared is the red line. So when you have, like, a clouds on top, like, you have this plateau, even through the night, which is very important. Like, so the infrared here is capturing that the night was clouded, right? All the other sensors are dead because, like, they are trying to capture, like, the solar irradiance, and, like, there is none at night. But the infrared is still, like, showing that, like, during the whole night and the morning, I had cloud cover. And then, like, the sky cleaned up, like, this particular day, so the temperature dropped, and then you go on. These are some of the instruments. This is, like, a little bit of an Escher composition here, because I hope you can see this. Like, there is a back picture of the station. Here you have, like, a tracker, like, with two shade disks, one infrared sensor that is shaded because, like, we don't want to degrade our sensor, like, having useless irradiance from the sun, because this is really long infrared, and one pyranometer shaded, like, to give us, like, the diffuse. And this particular stick here is the normal irradiance pheliometer, which is the instrument that measures, like, the direct normal irradiance. This is, like, ultraviolet sensor. Like, here we have the laser, the Doppler anemometer, thermometer, and so on. There's another tracker there. This is all one photograph there. This photograph is actually looking at these instruments from there. So, like, and you can see here the absolute cavity radiometer, which is the calibration standard for these DNI instruments. And this is inside this box, right? So, like, the way that it's mounted, like, it looks like an impossible figure. But so these are the instruments that we use regularly for our forecasting models, model development. So if a very important part of forecasting is, like, what kind of input selection and how do I work my training length. Like, so, like, I want to develop, like, artificial neural networks that are not going to be just curve fitting, but they will be able to adapt to new data that's going to come later. And we develop, like, like, I have an excellent PhD student who has been working on this for about 2 years, and he spends, like, 20 hours a day trying to develop the most accurate models and the most reliable training length methods to stop the training of the artificial neural networks. I'm showing here some data about trying to predict like a global horizontal over 6 days, this long-term forecasting. By the 6th day, there's quite a lot of error in the forecasting of weather. So like you can see, like there's a major jump. This figure here, like it gives about like a 20% root mean square error, which is very common for, see like first day we actually get the current day, we get like errors of about 10%. This is typical of 25. This line here of 25 would be typical for all satellite forecasting models for GHI. And for DNI, like you would be really here 35% root mean square error. When we do this, we can also look at the individual variables, like for example, sky cover, minimum temperature, probability of precipitation, and the cosine of z. This again is the solar azimuth. And we can study each one of these variables and see how much of these variables are actually including error in my final calculation. So all of this leads to results like this. This is the traditional forecasting model. So here, this curve, the bottom curve is for global horizontal, and the thick line is for forecasting at the current day, so ahead of time, but during the current day. And this is for the whole year, from November of 2008 to November 2009. And then you can see progressively as you go, this is forecasting 2 days ahead, and the error increases, but it doesn't increase that much until you get to 6 days ahead. And then is this really light line here. You can see errors of almost 50% if you're trying to forecast. It's slices of 1 hour, 6 days ahead of time based on the forecasting values that you have available from the weather. Direct normal irradiance, much more complicated. The errors are typically much higher because this is much more sensitive to cloud cover. And if you are in the winter, you can have very high root mean square errors. If you're in the summer, they drop to, this is a traditional forecasting method. It drops to about 20%, 25% root mean square error. These are the best that they can be done with these traditional methods. So one thing that we do is we focus a lot on the input selection, on treating the inputs. As it's obvious from these pictures, we were talking about R-squares of 99%. And very small root mean squares of the order of 3 to 4, 5% when we are doing modeling. And then when we start doing forecasting, even if you're doing only 1 hour ahead or one slice of 1 hour, 1 day ahead, you can make these errors a jump from 3, 4% to 25%. And in the case of DNI, they can jump to 40%, right? So it's not trivial. We have to be a little bit creative about it. So temporal delay dependency is important. It plays a role. Your artificial neural networks are trying to adapt to the changes, but sometimes they miss a major change, and then they keep trying to track this after the fact, which obviously doesn't help us if you are trying to do forecasting. So we need better input variables. These are all the variables that I can get from the ground, from the satellite, from weather, from the National Weather System. Network. So how do I create information out of the limited number of streams of data that I have? And how do I create information that is relevant for the forecasting? So one way that you can do this, you can use a traditional method, which is divided differences, moving averages, trying to create a time series that doesn't take only temperature in consideration, but let's say the divided differences of temperature or the first derivatives of temperature, the rate of change of temperature and the second derivative and so on. I can also integrate temperature and try to use this. These are traditional ways of treating with this problem of a limited stream of input data. So I need to look for time series that are relevant and carry historical information for my data. So how do we do this at the UC Merceds? So this is what our group does. So what we do is like we came away from using just the regular first, second derivatives, and we basically started using like non-integer derivatives in a very general way. Many of you may not be familiar with this. Everybody's familiar with the first order derivative, second order derivative. Everybody has seen this before. But if I ask like what's a half derivative, like many of you would say like I never heard of this. So a half derivative is the easiest way to explain like what this means is to say that like is the intermediate behavior, dynamic behavior between the zero derivative and the first derivative. So mathematically, like it's easy to see these like through Laplace transforms, right? Like if I have like the Laplace variable multiplying my transformed variable, I would get like in real space, like I would get my first derivative. If I have s squared multiplied by capital Y, I get the second derivative and some dependence on the initial conditions. So what if I have s to 1/2? Like then this would lead me to like a convolution integral, and that is really like the meaning of what like a half derivative would be. So it's easy to see this in Laplace space. If you are thinking about like a displacement, for example, that is where most of us like in high school like learn about first and second derivatives. You remember the displacement. If you take the first derivative, you will have the velocity. The second derivative would be the acceleration, right? So the zero derivative in this case of displacement is displacement itself. So 1/2 derivative would be something that is dynamically in between the displacement and the velocity. The same way, the 3/2 derivative would be something in between velocity and acceleration. So we use this, but we go a little bit further. Like instead of just using like a fractional or non-integer rational or irrational, we decided to actually use variable order derivatives. And this is a little bit more complicated because now the order of the derivative is going to change in time, or it's going to change, for example, with displacement or with displacement in time. And I have this graph here, like, and I'm going to try to talk about this in detail so like it's clear what it is. So here is I'm trying to take the t derivative of t. So like t is varying, and like I'm going to try to take the t derivative of the function t, right? So this is the function itself. So this is the zero derivative. I plotted here that there's a very thin, like a gray line, is actually the 0.03 derivative of t going along. Like I don't know, if I put 0.01, you wouldn't see it. This one here is the first derivative of t in time, so dt, which is 1. And here plotted is the 0.99 derivative. It's almost going on top of the first derivative. So all of these other curves here, this is the 0.25 derivative, the 0.5 derivative, the 0.75 derivative. So, but what I want is not like any of these constant derivatives, even if they are not integer. I want a derivative that changes in time. So I take the t derivative, and at any point, for example, at 0.03, like this would coincide with my 0.03 derivative here. At 0.25 would coincide with the 0.25 derivative, which is this curve, and so on, 0.5, 0.75, and so on. I can describe like this is like a general operator, it's what I call the restricted variable order operator. Restricted to order 1, but like I can expand this to any order, both negative and positive, and any function within like those orders that I decide. I don't need to apply this only to functions, because as you see here, the interesting part of this is that like this operator, all the derivatives that are not integer are non-local. So like you have like an integration, so like they are non-local. Like only the integer derivatives, like first, second, third, fourth, only these derivatives like actually kill the history to the point that like they become local operator. So here I take a derivative of the Heaviside function. So this is the t derivative of a unit step, basically. So you're coming here 0, and I can jump to 1. So the zero derivative would be 1 itself. The first derivative would be 0 here. And of course, like the first derivative at 0, like would be like a delta function there. So if I look at this, like these are my 0.99 derivative, the 0.75, and you can see like the trend. The interesting thing about this is that like if I take the t derivative of these, all of them blow up at 0, but the t derivative is defined throughout the whole domain. It starts at 0 because the zero derivative of the Heaviside itself, so it's 1. And like it moves along continuously. So not only the variable order derivative exists in the whole domain, it doesn't blow up at 0 as all the other non-integer derivatives do. I can go and do something more complicated. I can take the sine of 5t derivative of t cubed, and this is what happens here. Like I kind of bounded this by the t4 to the 4th, which is every time that this sign goes to minus 1, and and 3t squared, which is every time that this sign goes to plus 1. So this is what the derivative does. And if I become creative and I go beyond the limit between 0 and 1, I can take the 3 sine of 3t derivative of cosine of t. And you can see here that this gives a very simple operator, gives a very chaotic, it never repeats on a very periodic. Both functions are very periodic, the order and the function that I'm differentiating. So to do this now, so how do we implement this? So now I have my streams that I had before, and I have variable orders that may be functions or just fractional orders. And I have a genetic code that is competing for making all these neural networks that have these coefficients compete, and I go back and see are they forecasting well? And when they are forecasting well, the genes remain. If they are not, the genes are removed from the gene pool, or they stay dormant, and I keep interacting on this until I get a stochastic variable order model that now takes several different kinds of inputs and different versions of the inputs, computed them was controlled by a genetic algorithm, and now I get a very accurate forecasting. That I corrected a lot of the deficiencies that I had in the previous stochastic forecasting models. This is here, just to demonstrate, this is the average, a root mean square error going down as the generations of the genetic code grow. So this is for after 50 generations. This is a stochastic process. Every time you run the neural network, would give slightly different results. So this doesn't come in the regular plateaus that you see in GA applications. So I can go and do multi-objective optimization, and optimize both for the root mean square, the standard deviation of the error and the error itself. So I have a postdoc, Hugo Pedro, that did this very nice calculations where these are all points of different simulations. This is basically describing the gene pool of these different brains that we kind of evolved over time. And then this is the Pareto front. So there's an equivalence between the results in this Pareto front here. But I can optimize for having more of a prediction capacity or more of a curve fitting capacity. And as I go here, you can see we can capture with error bars, which is very important. I have so many different neural networks giving these results that I can easily run the statistics and find out what's the error band. The error bands here are in gray. And you can see this is very valuable for utility companies, by the way, because this is how you would decrease your spinning reserves by knowing what's the confidence level of your forecasting. And we can actually forecast very accurately. Now, if I go back and you may be asking, well, how effective it is to create these new streams of data input that have known integer values. This is after 50 generations, it's coming from 0 to 50 here, and these are just a very simple simulation where we used fractional derivatives from 0 to 2, and you can see that after 50 generations, the second derivative has a very small frequency in the final genome, in the gene pool, it doesn't survive. And the first derivative, doesn't survive at all. You have a little bit there in the beginning, but after 50 generations, not there. But, derivatives of order 0.1 and 1.5, are very strongly represented. So like these are the best derivatives for you to treat the input of the data that's being used in this particular simulation. And this is like not unique of one simulation. This is pretty much widespread. So what we are trying to do, like I know that I'm getting there, right? So what we're trying to do with this variable order evolutionary forecasting is, if I don't treat the data like, and I just apply a regular, forecasting technique, I would have a dispersion graph like this one. This is like a forecasted values of a DNI versus measured values, which is like all over the place, like there's error everywhere. So as I start treating the data, doing like what we did, our pre-processing of the data, I start getting much better results. But then when I finally develop the GA controlled artificial neural networks of variable order, I can get this error to actually go into the identity line. One more thing, maybe I can skip this. This is what we're trying to do, and basically using all these inputs our generic algorithm. We need a couple more $1 million to do that, but we are trying to build a forecasting center at the UC Merced, and then this forecasting center would feed information to the California ISO, utility companies, energy traders, power producers, and the end result of this is actually much cheaper solar. I ran out of time to talk about this. This is our campus. This is a solar array. We have a 1 megawatt solar farm, and we are applying our newly acquired knowledge about the solar resource in the Central Valley to manage the loads on campus. These are loads on campus there. This is the amount of energy produced by the campus. So if you start from zero, from midnight, you go on, and you get into the day, the load is high, but since we are producing, in the solar farm, you have this dip, and so on. This is a lot of stuff to talk about this here now that I'm running out of time. But basically, this is running from January to March. You see, in March we are getting more sun, and we are able to dip deeper during the day when energy is more expensive. In the winter, it's not that expensive, but during this time here, we are saving quite a lot of money for different reasons. I'm happy to talk with anybody that wants to discuss this. We're also using this to integrate into the management plan of the campus. And I don't want to finish before acknowledging, who, by the way, they are going to be here next week for the Big Ideas ceremony, on the poster presentation. Ricardo Marquez has been fantastic, in my lab. He's a PhD student. He does everything. He does, the instrumentation, the modeling, develop most of the work that is here. Hugo Pedro, is very recent postdoc, but he hit the road running. Dave Larson does everything for us. Anne Mahachek left after she helped us put the solar stations up. And these are my collaborators. These are mostly faculty, in several different campuses in different projects that we have that came out of, that they sprout out of the CITRIS CIMI project. Sorry, I went over time.
Great. I actually want to go see this. This looks wonderful.
Yeah.
So we're open for questions, and let's see, Gaiman, we have another mic. Why don't you take this one? And there's a question in the center there. And I'll go to the rest of the audience.
Hi. Just a couple of quick questions. So the chart where you showed your prediction, your predictive success based on these multi-order or variable order predictors, did that incorporate weather data, or is that just derivatives of the historical?
In fact, that incorporates less data than the previous predictions. We focus on a few streams, and we treated these streams with actually only fractional for that results. A variable actually give much better results, but there's a particular issue there, but it actually has less streams than the previous simulations. Just that you now have more you see like you have less physical streams, but now you have more treated streams. Like, I can take several different non-integer derivatives of those few streams.
Okay, but the data was historical data of like what the solar was doing at the moment, or was it weather as well?
Oh no, that's for the irradiance forecasting. So you mean the input variables or the input variables?
The
that
data,
one was only measurements from our station.
Okay.
It doesn't have. That's actually predicting power output from the power plant based on like a very simple measurements done at the station. Like it doesn't actually have any weather prediction there.
Okay. And then if I could ask just a second question, how did you get the idea or come to the conclusion that you wanted to look at these variable order derivatives? Like, what gave you that direction?
Well, this is an interesting story. Like, I have been working with this like since 2003. Like, when in a different problem, and I, developed this operator, and I was fascinated that like I could take any function and take any order derivative of any other function, and this would produce like complexity from a very simple operator. So when we start working on this problem, like after we had squeezed everything that you could possibly squeeze out of the neural networks, we had treated all our input data. We had more input data than anybody had ever attempted to use like to predict this. We still we could get substantially maybe half of the error of other simulations, but we couldn't go to that last like a 10% was almost like impenetrable. So then I had this idea. Well, what we need is like a better treatment of our input. Like what do we do with the input? So we tried different things. We tried like divided differences, and different forms of treating like a moving average, like the time series. Then I said, well, why not use non-integer derivatives, because they carry the history of that particular function. And when I did this, the first simulation that we did, really surprised us because it reduced the error substantially. And we are still in the process of perfecting. I got notice 2 days ago that I could talk about this. Like I have to include this in the last minute because we have a patent pending on the methodology. And I was finally filed, or they did a fantastic job in filing like this in a record time. But I got notice Wednesday that I could talk about it. So that's why I just threw some slides here on that. I was not going to mention it.
So I've been looking at solar data, trying to understand this from the grid integration point of view. And one of the things is that you can kind of get rid of a lot of this short-term variability by just looking at the aggregate of a bunch of solar plants. In a big
rooftop would be
rooftop, or just multiple plants, more than just a single one. So here you're focusing on sort of this one PV plant for UC Merced, but I think from the CalISO's perspective, they're going to be kind of more interested in the aggregate of all of the PV plants.
Actually, I went to the CalISO maybe 3 months ago, and it's true what you're saying. If you're talking about rooftop, you aggregate all of them, and then you go to the substation, and you don't really need to know the details of each one of the rooftops. But the local substations can also not take major drops. If you're talking about a 300 megawatt a power plant that they can drop in 60 seconds from 300 to 0, this would locally create a major imbalance. So everybody's looking for short-term forecasting for if you're using CPV, for example, and you're concerned about the inverters. That's a very important, even the 5-second forecast ahead is very important. So 5 second to 5 minute ahead is a window that California ISO is looking at. It is a bottleneck, in the form of the aggregator. The grid is not completely is one block that you can dispatch from anywhere. You can create instability locally. And that's a major concern if you have power plants of 1 gigawatt size.
Great. For those of you that have not been to the Merced campus, that's the campus swimming pool out in the back there. And so you really do need this array to heat that water in the winter. Thank you very much, Carlos. That was fast.
Thank you.